Hello, welcome to your bonus lesson on Introduction to Combinatorial Mathematics. This mathematics will help you answer questions something like this one. There's going to be a four-person committee chosen from 9 men, 3 women, and we want to know how many different committees are possible that have only 1 woman in the group. All right, let's begin. This is a little bit beyond our normal study of probability, but this lesson is based on a question that has been asked often by students. Let's go back to a question we've seen recently, where we had a bag containing 5 red and 3 blue marbles, and the 2 marbles were drawn simultaneously. That's the key word here. They were drawn from the bag at the same time. And the question here was basically looking at how the answer was set up. We have a tree diagram, and in the tree diagram it shows draw number 1, draw number 2. That seems to imply that you are drawing one marble and then the next. And the numbers in the in the tree diagram also show the same thing. So we're drawing a red first, so 5 out of 8 marbles are red, and then draw number 2. Now we have 4 out of 7 remaining marbles are red. So the number of marbles has decreased. So the implication there is that we have taken one marble out, now there's 7 left in the bag, and now we're taking another marble out. And that's strange, because it does not seem to match the word simultaneously here. This has been addressed in a previous lesson as well. In probability, simultaneously, how we calculate that and whether we think of it as 2 things happening at once or one thing happening after another, like is shown here, it actually has no difference in terms of how we calculate it. So that's why the answer is shown like this. But there's still that discrepancy there, which is kind of troubling or maybe difficult to understand when you first learn probability. So let's take a look at some more details in this. Okay, so again, I think an easier way to look at this is rather than calling these draw 1 and draw 2, let's think of them as left hand, right hand. So your left hand and your right hand reach into the bag at the same time and pull out some marbles. So if you think of it that way, maybe it doesn't seem as much as one thing happening and then another, because both your hands go in together. So your left hand has a 5 out of 8 chance of holding a red marble and a 3 out of 8 chance of holding a blue marble. And then your right hand obviously can't grab the same marble, and there it's grabbing another one in the bag, but at the same time, and now it has a 4 out of 7 chance. So the other hand has less marbles to choose from because the first hand is grabbing a marble already. So that's one way to look at it, but still doesn't really get at the heart of why simultaneously can be represented like this. But let's take a look, and as we go forward, you'll see how all this becomes more clear. So the probability we're looking for is the probability of drawing at least one red marble. And at least one red means, well, either a red-blue or blue-red or both reds. All those situations show at least one red. So looking at the tree diagram, that is your red-red path, your red-blue path, or your blue-red path. So 3 of these paths, 3 of the possible 4 paths lead to this answer. But as we saw before, we can't just say then the probability is 3 out of 4, even though it's 3 out of 4 paths, because each path has all these different probability values. So what we have to do is multiply the probabilities along one path, basically saying this happens, then this happens, and then add up those 3 paths. So here's your first path, 5/8 times 4/7, plus another path that leads to 1 red, which is 5/8 and 3/7, and then the third path plus the third path that leads to 1 red, which is this path here. Add all those up, you get 25 out of 28. But let's take a look at the fraction before. Actually, when you multiply those and add them up, you can see the denominator is 8 times 7, which is 56. So we end up with a fraction, something out of 56 first. And if you add up those numbers, it looks like 50 out of 56. And then that has been reduced. So let's think about that number, 50 out of 56. Okay, so what we have here is a sample space diagram representing the same situation. As mentioned in a previous lesson as well, we can draw sample space diagrams anytime we have a compound event, which this is made up of 2 smaller events. And there are only 2 smaller events here. That first draw, second draw, or that left hand, right hand, the 2 marbles. So here's marble 1, here's marble 2, here's all the possibilities of marble 1, the 3 blues and the 5 reds, and here's all the possibilities for marble 2, the 3 blues and the 5 reds as well. Notice though in this sample space diagram I shaded out the middle values here. The reason for that is these are not, basically, yeah, if you look here, this would represent blue blue marble number one and blue marble number one. But it's impossible you're holding that same marble and calling it two marbles. So you cannot call the same marble the two marbles. So I've eliminated all those things here. Now we're left with a sample space that's a little smaller than what we see. If we multiply these numbers, there are 8 options here, 8 options here. So 8 times 8 would give 64. There are 64 total options there. However, subtract those ones I just mentioned, which is 8 of them. So 64 minus 8 is 56 total options of what we could be holding in our hands in terms of marbles. And then we think of which of these represent at least one red. So I'm going to shade those. All these shaded boxes represent at least one red marble. For example, blue number one and red number one. That's at least one red. Or for example, red number 4 and red number 2. If we're holding those two, that's 2 reds, so that's at least one red. The only place we don't have at least one red is here, where it's like holding 2 blue marbles, holding 2 blue marbles, and so on. And that is 1, 2, 3, 4, 5, 6. So 6 out of the, I said 56, do not meet our criteria. So to get at least one red, we have 50 out of the 56 possibilities. And notice that matches this. I think that's an important connection to make, to see that this tree diagram and this idea of simultaneously, all that can be represented like this. And anytime we talk about probability, we can create a sample space. We might not be able to create a two-dimensional sample space diagram, but we can also always create a sample space, which is basically a list of all the possibilities. And if we have a list of all the possibilities, we can see how many of our possibilities meet the condition we need and how many that is out of the total possible, which is 56. So that's an important connection there, and that reduces to the same answer. That still doesn't really get at the heart of the simultaneous thing. So now I'm going to take this lesson a lot further, and it might have to be a two-part video. But if you are along for the journey, welcome and congratulations for taking on this bonus content, because what you're going to see now is beyond our course, but will certainly help you with some DP work in the future. Let's begin. All right, let's begin at the beginning. This is called the fundamental counting principle. Here's an example. To make a gift for your friend, you can use pink or green paper and marker, pen, or pencil. How many different types of cards can you make? So a tree diagram for this could look like this. You're making a card, you have a choice of paper first, pink or green, and then after you've chosen paper, you can choose marker, pen, or pencil. So you can see now there are 6 paths that you could follow to their end. So there are 6 possible events here, or 6 possible outcomes. So that is all the possibilities. Now, showing that in what's called as a fundamental counting principle, we can look at it this way. We have a choice to make. First event, paper, and we have 2 choices. And then we have a choice to make a second choice. So this is like a compound event. And the second choice is writing utensil, and we have 3 choices for that. To figure out how many total choices or how many paths there will be here, we do 2 times 3. Simple idea, but you'll see how this grows into something much bigger soon. So 2 times 3, 6 total outcomes. I guess it shouldn't say events here, 6 total outcomes, because these are compound events. All right, and each of those is equally likely. We don't have any probabilities written here, so we're just going to assume it's a 50-50 chance everywhere we go here, 50-50, and then here like a 1/3, 1/3, 1/3. And since all the probabilities are the same, all these paths have an equal probability, and that means that each path has a probability of 1 in 6 because there are 6 paths. Okay, again, simple example to begin. Let's see this go further. So here's another one. When you get ready to get dressed for school, you open your closet to find that you have the following choices: a red, blue, or white shirt, then jeans or sweatpants, then tennis shoes or sandals. How many different outfits could you make with these choices? So see if you can sketch a tree diagram for that, and then you'll see how many paths there are. Then see if you can figure it out using the fundamental counting principle, which is just the multiplication thing we looked at, and figure out what is the probability of one outfit, and then what is the probability of an outfit that has a white shirt. Okay, let's check. So first, you're choosing your outfit, and you first choice shirt color, red, blue, white, and then jeans or sweatpants coming from each of those, and then tennis shoes or sandals from each of those. If you follow all those paths and you count how many final possibilities there are, there are 12 paths in total, so 12 possible outcomes. For example, white shirt, jeans, and sandals. That's one of the 12. So 12 possibilities. Using fundamental counting principle, we put our 3 events here: the event of choosing a shirt, the event of choosing pants, and the event of choosing shoes. And we just multiply those 3 numbers. So it's like 3 times 2 times 2, and it shows you how many possible outcomes or how many ends to this tree diagram there are. So 12. Same result here, same result here. So probability of one outfit is 1 in 12. Again, we are assuming your probabilities of choosing these is random and therefore equal. So you have the same chance of choosing red, blue, white, and so on and so on. 12 events, so one outfit has a 1 in 12 chance. Therefore, probability of choosing an outfit with a white shirt is looking only at the white part here, and at the end of a white shirt, you have 4 paths that branch out from the white shirt. So 4 of the 12 outfits are white shirt outfits, therefore 1 in 3. Fantastic, here we are. We have arrived at permutations. There are certain exciting times in your life, for example, your wedding day, your birthday, and maybe some other events. This is now one of those. Welcome to permutations. Permutations. One ordering of a specific set of objects is called a permutation. Here is a formula for permutations. There are some new symbols there. Let's get acquainted with those. This means n choose r. Expanded, this formula is written as n factorial over n minus r factorial. All right, so again, this part we read as n choose r. This part is read as n factorial. A factorial is pretty simple. Here's how it works. If we have 3 factorial, that means 3 times 2 times 1. All right, so for permutations, key point, key point, key point, the order matters. The order is essential. On the graphing calculator, to get factorial or to get permutations, this thing here, you have to press the math button, then scroll over to probability, and you will find this and this very quickly. Okay, let's see how this all works. Again, keep in mind, for permutations, order matters. Here's what we're talking about. Let's say you arrive at home and you have 4 shows waiting for you on your TiVo. Wow, this must be an old problem. I don't even know what a TiVo is, and you probably don't either. But there are 4 shows. One is Family Guy, one is American Idol, one is Gossip Girls, and one is 30 Rock. Again, I think we're like 10 years behind the times here, but that's cool. All right, you have time to watch all 4 shows. List some permutations. Again, permutations is a selection of items where the order is important. So some permutations of this would be this, for example. FIGR. So you watch Family Guy, then American Idol, then Gossip Girls, and then 30 Rock. Or you watch Family Guy, then Gossip Girls, then 30 Rock, then American Idol, and so on and so on. So you are watching all 4 shows, you're just reordering the order you watched them in. These are all called permutations because the order you've chosen to watch them in matters to you. So those are all the ways to count how many ways you can watch all 4 shows. That list will go for a while. Let's see how much it is in just a minute. Now, let's say the situation changed and you only have time to watch 2 of the shows. Let's list some permutations here. Well, one pair of shows you could watch is Family Guy and American Idol, or Gossip Girls and 30 Rock, or Family Guy and whatever. Or you can reverse these as well. You could do American Idol and then Family Guy. That's considered a permutation also because the order is important to you. So even though it's the same 2 shows, watching one first or the other next, it matters to you that order. So those are all called permutations. It's basically a count of the ways that are possible. Okay, so let's move on. So looking back at the watching all 4 shows, we're going to use the fundamental counting principle, which we've talked about, to find the total number of permutations. So here's how we're going to do it. You have these 4 slots in your life, and you're going to watch a TV show in each of those slots. So for your first slot, you have 4 choices. There are 4 shows to choose from. All 4 are available. Next slot, there's only 3 shows available because you've watched 1. Next slot, there's 2 available. Last slot, there's only 1 choice you can make for the last slot. Multiply those, 24. So that, looking at this, if you were to list all the possibilities here, all the permutations, that would be 24 of them. Now, in terms of using the permutation formula, this is the one that was given to you here. So we have 4 shows and we're choosing 4 of them. So 4 choose 4. That P means we're going to do a permutation. So the formula, you put your number of things you're choosing from here, then you do those two numbers subtracted each other on the bottom. So 4 factorial, again, is going to be 4 times 3 times 2 times 1. 4 minus 4 is 0. By the way, 0 factorial is 1. And if you want to see why that is, you can find lots of stuff on the internet about that. Very interesting. So 0 factorial is 1. So here, essentially, we have those multiplied over 1, which is the same as here. And we're back to 24. So there are 24 ways to watch these shows. Let's look at the 2-show situation, where you have the 4 shows, but you only have time to watch 2. And again, the order you watch them in does matter to you. So we started listing the permutations. Let's see what they all could be. Using fundamental counting principles, we can go like this. You have one slot where you're going to watch one show, and another slot where you're going to watch another show. You're only watching 2. So there are 4 possibilities for that slot, 3 possibilities for that slot. Multiply those, 12 possibilities. So if you were to list all these, there would be 12 different possibilities. Using the formula, now we have 4 shows to choose from, and we are choosing 2. So 4 factorial, the number we have to choose from, then subtract those 2 numbers, and that goes in the denominator. 4 factorial, again, multiply those. 4 minus 2 is 2 factorial, so it's 24 over 2, 12. So now there are 12 possibilities if you're to watch only 2 shows. Okay, so that's a basic introduction to permutations. The next step is combinations, but that will come in the next video. So hope you learned something there. We still have not come all the way back to that first problem we had, which was looking at grabbing 2 marbles from a bag simultaneously. This is that problem is what inspired this whole lesson here. So please come back for part 2 of this bonus video content, and you will see how we circle back to that problem. See you soon.